A mapping survey collects the information we need to make maps. Maps can be enormously valuable for decision making. For example, in modern agriculture, we can use maps to analyze the shape of the land surface and to plan drain tile systems like you see here. We pay close attention to surface slope to produce efficient, reliable systems. You learned that slope is a ratio of rise over run. Rise is a change in elevation, that is, a vertical distance, and run is a horizontal distance. Measuring horizontal distance is simple with a tape or with a measuring wheel. But how can we measure the vertical distance, that is, the rise between the points shown here? Well, that vertical distance is best found by a process we call leveling. To most people, this is a level. More specifically, this is a carpenter level. It has a bubble tube that indicates which end of the level is higher than the other. Well, how does it do that? You see, the bubble moves in a curved tube like you see here. That's a very flat curvature. As the tube tilts, the buoyant bubble rises to the highest possible position within the tube. Now, if I can hold the carpenter level steady with the bubble centered within the marks, both ends of the level will have the same elevation. Here you can see that the concrete surface at this end is higher than the concrete surface at the other end of the level. The underside of the level is now a reference line we can use. With the bubble centered within the marks, I can measure down from the underside of the level to the concrete. This measurement is 0.18 feet. Since the other end of the level sits on the concrete, the vertical distance between the two ends is 0.18 feet. By repeating this process over and over, adding measurements end to end, we could find the vertical distance between two distant points. But that becomes very impractical as the horizontal distance increases. So, instead, for leveling surveys, we use instruments like these. This is an optical level. It's basically a telescope that can be oriented to create a horizontal or level line of sight. Well, how does that work? The level telescope contains a crosshair. The horizontal crosshair defines a level plane in all directions. That is, your line of sight through the horizontal crosshair is a level line, perpendicular to gravity. Just like the underside of the carpenter level was held level just a few moments ago, now your line of sight is level. Because the optical level is telescopic, you can see farther. If you can see farther, then the distance between your measured locations can grow. To measure elevation difference with an optical level, we also need a level rod. This one is graduated in decimal feet upward from 0 at the bottom. The difference in two rod readings taken from the same instrument location equals the elevation difference.
Now here are some examples of optical levels. This dumpy level was made around 1915. Notice how long the telescope is. Using the 4 adjusting screws in the instrument base, a surveyor would level the instrument in 2 directions, centering the bubble in its cylindrical tube.
The tilting level represented the next generation of leveling precision. This one was manufactured in the 1940s. As optical science had improved, it sported a shorter telescope and it had an innovative feature that allowed more precise leveling: the split bubble. Below the long bubble tube, an adjustable mirror reflects light into the fluid and bubble in the cylindrical tube. Using a separate eyepiece and another internal mirror, the operator views two halves of the bubble image and adjusts the level carefully to align the two images. Introduced in the 1950s, the automatic level contains a set of tiny mirrors that move automatically in response to Earth gravity, ensuring that the instrument line of sight is perfectly level. If the instrument settles during use, this automatic compensator simultaneously adjusts the line of sight back to the horizontal plane. Here you can see the top of the mechanism moving as the instrument is tilted. Because they contain compensators, automatic levels can give greater precision than older uncompensated instruments can. With the advent of inexpensive laser devices, the rotary laser level has made some leveling surveys possible with only a single surveyor. A revolving mirror produces a horizontal plane of laser light. A laser detector on a special leveling rod enables measurement at each desired location. Farm drain tile installation equipment commonly uses a laser plane to control the pipe depth, ensuring proper slopes and efficient drainage. For high precision, digital levels with advanced internal compensators read the barcode on a special rod while simultaneously collecting atmospheric pressure and temperature readings. Each of these methods creates a horizontal or level line. Using this line, just like we used the underside of the carpenter level, we can find elevation differences, but with a telescope or with a focused beam of laser light, we can extend that line much farther with greater precision.
So far, you've seen the main tools we use for leveling. In the next video, we'll explore the basic processes of a leveling survey. I'm Todd Horton for the Illinois Professional Land Surveyors Association.